Hello and welcome back. We now know how to balance redox reactions, and we're going to use those to make electrochemical cells moving forward. So what do we got to do? We have to know a little bit about some of the numbers that are going to be involved in the calculations that we're going to be making. So on the first slide, it's kind of odd. I'm just going to present you a bunch of numbers and talk about them, and then we'll kind of use them as we go through. I kind of like to have them all in one place rather than kind of doing them as we go because they're somewhat related to one another. So the first number that we have to know, and by the way, you don't have to memorize any of these for my class or anything like that, but you do have to be aware of them and how to use them when you need them. Okay, so charge on an electron. What is the charge on an electron? Well, we know it's negative, right? Charge on an electron is negative. However, when people talk about the charge on an electron, they rarely put the negative sign. And charge is measured in coulombs, and it is 1.602 times 10 to the minus 19th coulomb. So not a lot of charge on a single electron. I mean, just imagine a single electron going through. It's not very much charge. But you get a mole of electrons, you multiply 10 to the 19th minus 19th by 10 to the 23rd, you're starting to talk about, tens of thousands of coulombs. That's a good thing. Okay, what is an amp? An ampere. You've probably heard that unit before. Oh, this is a 3 amp, or this is a 500 milliamp, or things like that. What is an amp? It's got a definition. People usually use a capital A to represent the amp, and it just means coulombs per second. So 1 amp is 1 coulomb per second. It's a coulomb of charge, which is the charge on 10 to the 19th electrons. So the coulomb of charge every second. So 1 amp is the equivalent of about 10 to the 19th electrons every second. So when you have something and this is a 1 amp circuit, you're moving about that many electrons. The funny thing is and when you get down to the milliamps, it's not that much less. It's 10 to the 18th, 10 to the 17th, 10 to the 16th. Still a whole lot of electrons moving through every second. Now, you can actually quantify that if you want. It's 6.24 times 10 to the 18th. Well, that's an awful 6. Let me fix that. 6.24 times 10 to the 18th electrons per second. Not a number we're ever going to use, but just an interesting one. All right, what else do we know about circuits? Well, we measure the current, how much electrons are flowing. We also measure the voltage. What do we mean by the voltage? Well, we also mean what's called the potential difference. These two are fairly synonymous, voltage and potential difference. And the unit of that is generally the V. Capital V is volt, but it's actually a couple units that we are now familiar with. It's a joule per coulomb. So it just says how much energy is in every coulomb of electrons. Okay? That's all it is, right? So the bigger your voltage, the more energy 1 coulomb has. The smaller your voltage, the less energy 1 coulomb has. So a 12-volt battery can run the same current. It can run maybe an amp of current as a 120-volt battery, but the 120-volt battery is going to have 10 times the energy because it has 10 times the voltage if it's running the same current. Okay. Now, in batteries and in electrochemical cells, we're also going to call this the cell potential. So they are all just synonyms of each other. And that's what we're talking about. Okay, so it's just energy over charge, right? So voltage is essentially energy over charge, or you can arrange that and say that energy is voltage times charge. Now, that's a neat way of calculating the energy that you have. You take the voltage and you take essentially how much charge is going through, joules per coulombs times the number of coulombs. And we'll use that occasionally here and there. Okay? Another one that we'll use is what's called the Faraday constant. Now, newfangled books often tend to abbreviate this with just a capital F, which is kind of funny, but really, really fancy ones will make a nice big cursive F like that. And it's the charge on 1 mole of electrons. I mentioned that earlier. It's going to be in the tens of thousands. And in fact, it's 96,485 coulombs per mole. And that one we will use actually quite a lot. We're going to use Faraday's constant because it will appear in several equations that we use when we're trying to talk about these things. Let's say we wanted to know the total charge that is passing through. Q, capital Q here, is N times Faraday's constant, right? You want to know exactly how many coulombs of charge you're getting. You just take Faraday's constant, you multiply by moles, it gets rid of the moles, and you've got coulombs. So we're going to use that too when we derive something. It's just total charge is just the number of moles times Faraday's constant. And you can plug that into the E equals VC, right? In this case, the V and the C are the same here. We're both talking about charge, and you say that E is equal to V times N times Faraday's constant. And so now we're relating the voltage not just to the charge there, but to actually how many moles of stuff are transferring. Now you can start to see where it gets a little bit more towards what chemists like. We like mole as a unit, and so we're going to use that in order to relate the total energy to the charge. And you can guess that this total energy might be related to Gibbs free energy, the amount of energy we can do stuff with, because that's what we do with batteries, right? We use them. So this was just a collection of kind of random things. And like I said, we'll pull from it here and there. Don't worry if these didn't make too much sense to you right away. I have to pause a moment and say that there's a lot of students and sometimes instructors who are like, oh, you know what, I don't feel like paying attention to all the details of this. I can get pretty close if I just have a vague sense of what's going on. The equations end up not being too hard, but you know, it's this minus this or this minus that. And you know, if I get it backwards, I'm just going to get a negative. You know, it'll be fine. I'll get lots of partial credit. But it turns out if you don't pay attention to all the details right now, there's several steps that you can make a mistake on. And each step, right, it's just a negative sign. And so you got a 50-50 chance. So it turns out you can mix up your anode and your cathode. And if you mix those up, you're going to mix up some other things. But you know, you got a 50-50 chance of getting it right. So you're like, 50-50, I'll take it. Okay. But then if you mix up the anode and the cathode, you might also assign the wrong sign to the potential for the anode and cathode. So, and there's a 50% chance of that too. So now you've got a 50% chance getting it right times a 50% chance of getting it right. Your chances are only 25%. But it turns out then you have to subtract one from the other. And if you don't subtract the right order, then not only do you have the sign wrong, now you've got a 50% chance and a 50% chance of, you only have a 12% chance of getting this problem right. So we really do have to pay attention to all the details unless you want a grade of 12%. Yeah, I didn't think so. So, got to pay attention to the details. What are the signs on all these things? It's going to be really important to keep track of those negatives and those positives and what they mean, subtracting the right thing from the wrong thing, all that kind of stuff. We're going to be a little bit meticulous in this chapter in order to get these right. All right, so finally, we're here. We want to make a battery, and we want to do something with it. But as you know, batteries have voltages. You go out and get your little AA battery. I don't know, I usually have some sitting around on my desk because my kids put them there. But you know, you've got your AA battery. It's, oh, there we go. A little Amazon advertisement. Amazon rechargeable batteries. About 1.5 volts, 1.5 volts. But then you can get the 9-volt battery. And guess what the voltage of the 9-volt battery is? Yeah, it's 9 volts. It's in its name. Okay. It's like a call-in show once did a, you know, what are the hours of the 24 Fitness in Toledo, Ohio, or whatever. And people called in and said, 6 a.m. to 7 p.m. Well, it's called 24-hour fitness. Anyway, right, we have 9-volt batteries. There's a 12-volt battery in your car. You can get all sorts of voltage batteries. So how do we know the voltage when we make a battery? Because we don't want to just guess. Okay, so how do we know the voltage when we make a battery? Is we need to know both parts of the battery. If I just say, oh, what's the voltage if I have a battery that oxidizes copper? We say, okay, well, let me go ahead and just oxidize copper. See what it does. Copper's like, hello, I'm trying to give away a couple electrons. Anyone out there want to take them? No. So you can't just oxidize copper all by himself. You can't just like, boom, and then figure out how energetic that is. Right? We need both an anode, something oxidizing, and a cathode, something accepting it. Right? Because you could have a really enthusiastic anode, like, please take my electrons, I'm going to throw them at you. But your anode's like, fine. And right, that's going to have one potential. But you have the same anode throwing electrons down. You've got this anode that's like, cathode that's like, oh, please give me those electrons and sucking them in. Right? That's probably going to have a little more energy to it. And so we have to know not only the cathode, not only the anode, we have to know both the cathode and the anode before we can know anything about the energy that's present. Because an oxidation-reduction reaction requires oxidation and reduction. You can't just do one of them. Okay? But then it turns out it will get really, really difficult to keep track of all the possible batteries in the world and be like, well, gosh darn it, I just have to, list every possible battery ever and calculate the voltage of that experimentally, and then I'm going to be able to publish that and be like, okay, if you want to know, a lithium battery, a lithium and a fluoride battery, it's going to make exactly this much. Or, wow, that would be a huge table. But it turns out that there is an intermediate that we can use. And we'll see that in just a moment. But the important thing to remember is that these cell potentials that we're doing are always a comparison. They're always a comparison. I can't just say, here's how much energy copper creates. I say, here's how much energy copper creates when it's paired with something. But it turns out what we do is we always pick the same thing to pair it with, which is what's called the standard hydrogen electrode. We'll get into the details of that in a moment. But the standard hydrogen electrode, and we say, oh, copper produces this much energy compared to the standard hydrogen electrode when we oxidize it, and nickel produces this much energy compared to the standard hydrogen electrode when we do it. And so it turns out, by comparing always to the same thing, even if we've never once in our entire life measured how copper and nickel interact as a battery, since we've compared them to the same starting point, we can say something about how they interact with each other. Let me give you a quick example. Like, we've got some stairs here, and we're going to compare everything to stair number 2 right there, which is that. So we've got one thing, A is here, and B is here. And we say, oh, B is one stair lower than my dot. A is one stair higher than my dot. So without knowing exactly how different A and B are, I can say, oh, A is 2 stairs higher than B. Same thing if I move A up here. A is now 2 stairs higher than my dot. You're like, okay, well, 2 plus 1 is 3. It took me a long time to get that. And so I say, oh, B is 3 times higher. But let's say, I had stairs here. Oops, not dot, I want B. And I say, oh, B is 1 stair higher than my dot, and A is 2 stairs higher than my dot. Then you'd all be able to say, well, A is 1 stair higher than B. So we can do all these kind of things, and as long as we're always comparing to this same thing, my dot there, we can actually compare things that we've never compared before. So that's what we do. We go out into the lab and we measure a bunch of cell potentials against the standard hydrogen electrode. So we stick copper on one side of a half cell, and we stick the standard hydrogen electrode on the other side of the half cell, and we measure that potential. We take nickel, we stick it on one side of the standard hydrogen electrode, and we put the standard hydrogen electrode on the other side, and we measure that potential. And by doing the correct math, we can now get the difference between copper and nickel. So you can kind of see where this is going. And that's a really useful thing. So what is the standard hydrogen electrode? It's just something somebody decided upon. It has no particular meaning in and of itself. It's just we had to pick a reference. Let's pick that one. Now, I'm sure there's a great reason that people picked that one, and probably had to do with being able to make it scientifically and make it easily reproducible and all this kind of stuff. Great, but that's just the reference we have to know. And what the standard hydrogen electrode is it's the conversion of H plus 2 electrons into H2 gas. And so you're going to set up that on one side, you're going to set up whatever you're going to measure on the other side, and you can always get these potential differences all relative to the same point, which means you can compare two things very, very easily. So how are we going to determine the voltage of, say, nickel and copper? Well, it turns out if you want to calculate what we call the cell potential, and we're going to start by doing those, we're going to start by doing those at standard states. You remember that circle there just means standard state. It's 1 molar for any concentration, 1 atmosphere for any pressure, and 25 degrees Celsius. That's all that little dot means. It doesn't mean anything else. It just means I have these concentrations, this pressure, and this temperature for all the work that I'm doing. And here's what you do. You just look up the standard cell potential of your cathode and the standard cell potential of your anode. And you subtract the two. How I remember this one is the state I learned this in was in California. And so I have Ca, C minus A. If you're coming from out of state, you just say those crazy people in California, and it'll work just as well for you. All right, so Ca, cathode minus anode, that's how we do it. So we do have to know what the cathode is, and we do have to know what the anode is. And we'll figure out how to figure that out in just a moment. But that's how we can calculate the standard cell potential. And so we can say, oh, we've got these two things. I take 1 and I subtract off 0.5 or 0.25, and so I get a 0.75 volt battery. That's all we're going to do, right? Just like I say, oh, A is at 2, B is at 1. I take 2 minus 1, and I say, okay, that's the difference between A and B. Very, very similar to that situation. Situation. All right. So what does the SHE look like? Well, it looks like the standard hydrogen electrode. What it is, you've got some H plus in solution, usually provided by hydrochloric acid. You've got a test tube of sorts with 1 atmosphere of hydrogen gas in it. And then you've got a platinum electrode down in there, which is acting as your electrode to transfer those electrons out of the standard hydrogen electrode. So that's what it looks like. And you're going to put that up against something you want to measure. So let's go ahead and measure zinc. And I'm going to tell you that zinc ends up oxidizing. This guy ends up reducing. And we know that from the voltage here. Right, the voltage here is 0.76 volts. So my 0.76 volts is the cell potential of my cathode minus the cell potential of my anode. Well, which one's my cathode and which one's my anode? Well, we know that the thing that gets reduced is your cathode. The thing that gets oxidized is your anode. So in this case, since we saw reduction on the side of the standard hydrogen electrode, that reduction must be my cathode. Now, how do I know the cell potential of the standard hydrogen electrode? Well, you know the standard cell potential of the hydrogen electrode by putting it against a standard hydrogen electrode. And if I have a half cell with something on one side and the exact same thing on the other side, how much voltage do you think that's going to generate? Yeah, 0. So in this case, we have 0 as that, and so this is minus E naught of my anode, and that is equal to 0.76 volts, which means the standard cell potential of my anode is minus 0.76 volts. Okay? And that minus just means relative to the standard hydrogen electrode. It is a negative value. Okay? And that's for zinc, going to zinc 2 plus. Okay? So that is my standard cell potential. Now, here's the funny thing. This is also what we call the standard reduction potential of zinc. And that should give you pause because you're looking, you're like, wait. When I look up that screen there, I look right up there. It's just right over there, Professor Clements, and I see that zinc is being oxidized. So didn't I just calculate the standard oxidation potential of zinc, not the standard reduction potential? You just said the wrong thing, okay? I'll forgive you because, you know, you're tired. No, I said the right thing. Why? Because it turns out we subtracted, right? And that subtraction is what made sure we were talking about reduction potentials, okay? That negative and the positive, reduction and oxidation are essentially just opposite reactions, right? You just reverse the reaction, you flip it around. And it turns out when you flip the reaction, you also flip the sign of the potential. And so if we added cathode and anode, then I would add the standard reduction potential of the cathode to the standard oxidation potential of the anode, and I'd get my cell potential. But we don't like to do that. Why? Because it's much easier just to pick a standard. Be like, I'm always going to list standard reduction potentials, even when things are getting oxidized, so that I only have to have one table. Right? Because otherwise I'd have a table of standard reduction potentials, then I'd also have a table of standard oxidation potentials. Or even worse in a situation, I'd just have one table, and then I'd have to remember to put negative signs on the things that were oxidized. Right? So what I do is I just say cathode minus anode. That negative sign on the minus anode is what takes care of reversing it, essentially, even though it's a standard reduction potential, by negating it or turning it into a standard oxidation potential. But never have I in my entire life seen a standard oxidation potential table. I've only seen standard reduction potential tables because that's just what people tabulate. Okay? So even though zinc's getting oxidized, we calculated its standard reduction potential, and that's the only thing you'll ever use is the standard reduction potential of things. Now, it's negative. What does that mean? What does it mean to have a standard reduction potential that's negative? Well, what did zinc do? Did zinc get oxidized or reduced? Okay, it got oxidized. So that negative, which means the other one got reduced, the standard hydrogen electrode got reduced. So what we're saying is here, this negative standard reduction potential says it's less likely to be oxidized than the standard hydrogen electrode. I'm sorry, less likely to be reduced, I should say. That one I did get wrong. Less likely to be reduced than the standard hydrogen electrode. What do I mean by that? Well, we know it got oxidized, and the other one got reduced, right? Which means the zinc must be less likely to be reduced. Okay, so more negative reduction potential actually means more likely to oxidize. More positive reduction potential means more likely to reduce, which kind of makes sense. I mean, the positive part makes a little bit of sense. I've got a large standard reduction potential, meaning I'm likely to reduce very well. All right, so moving on. Now that we've got this set of standard reduction potentials, we can combine things that maybe we've never measured before. Now, of course, all the things we're going to be talking about are things people have measured before. We're not going to be talking about anything complicated, but it does allow us to talk about complicated things that we've never measured before or haven't measured yet. So we can make predictions about what might happen in the lab. So let's look at a system where we've got a couple irons and 3+, and I've got my copper solid and copper 2+, 2, Fe 2+. So there is a redox reaction that we're going to try to use as an electrochemical galvanic cell. And what do we see? We've got Fe 3+ going to Fe 2+. So is that an oxidation or a reduction? Hopefully you came up with reduction. And we've got Cu solid going to Cu 2+. That is an oxidation. We should put our phases over here just to be thorough here. Okay, so we've got copper being oxidized, iron being reduced. So let's go ahead and look up the standard reduction potentials for each one of these, because that's all you're going to find. There's a table of it that you're going to be provided with, and you're going to use anytime we're doing homework and things like that. You're used to having those tables. It's just another part of that table. So what do we have? The reduction potential says that iron 3+ adds 1 electron to go to iron 2+. That is a reduction potential. And that's actually what we're doing here. We're reducing iron, so that's great. And so we looked that up. The standard reduction potential is 0.77 volts. Okay, oops, I don't know why I did that. Then we're going to look up the standard reduction potential of copper. But it's being oxidized, and this really bothers me. I got it. I totally understand that. You're right. Copper is being oxidized. But you're not going to find a standard oxidation potential table. So you have to look up the standard reduction potential of copper. So you have to look up Cu2+ plus 2 electrons goes to Cu solid. Okay? That's just what you have to look up. And you're not going to get around that because there's no such thing as a table of standard oxidation potentials. All right, so what do? We look that up, and we get E0 equals positive 0.34 volts. I'm going to specify that other one as a positive as well. So both of these are actually more likely to reduce than the standard hydrogen electrode. They're both positive. But how about compared to one another? Right? One has the potential to reduce of 0.7 volts. One has the potential to reduce of 0.3 volts. Which do you think is more likely to reduce? Well, let's look at the actual reaction we wrote. Iron is the one that got reduced, and iron is the one with the higher cell potential, or higher reduction potential, sorry. That's very interesting. All right, so how could we actually calculate the cell potential? E cell is going to be my E cathode minus E anode. So people will do cath and an very frequently, or C and A also, you'll see that. Okay, what do? Well, We figure out which one's our cathode. The cathode is reduction. Who's getting reduced? That was our iron. 0.77 volts minus 0.34 volts. If I do that math, I get 0.43 volts, which means if I hook this cell up, right, I've got copper on one side, I've got iron on the other side, I hook that up, put a wire across, put a voltmeter there to measure the voltage, I should get 0.43 volts if everything is at standard conditions. Okay. That's what I should get. All right, notice. I want you to notice something very, very, very important here. Very important. Pay attention. Stop it. Pay attention. Okay, the cat video can wait. I know you're trying to watch both at the same time. This one's important. Notice something. In our balanced chemical reaction, we had a 2 here, and we had a 2 here. We did not have a 2 there in our standard reduction potential. We also did not put a 2 here next to the standard reduction potential. When you are calculating cell potentials, the stoichiometry in your balanced chemical reaction does not come into play. You literally just look up the standard reduction potential for iron, even though you have 2 irons, and you put that into the equation. We'll see why later on when we compare this to delta G. It's kind of built in. It's kind of built in already. It's crazy that it works. Honestly, I still get like, really, that works? That shouldn't work, but it does. So even if you had something that was doing 1 electron, something that was doing 7 electrons, you don't put a 7 anywhere. If you had one that was doing 2 and one that was doing 9, you don't put 2s or 9s or 18s anywhere. Nothing. You just look up the standard reduction potentials, you write them down, you subtract them. Okay, it's a very important thing. All right, let's do another example. Here we're going to look at a cell of aluminum and magnesium going to aluminum and magnesium, but in slightly different forms. All righty, so who's being oxidized? Okay, hopefully you came up with magnesium going from 0 to 2 plus as an oxidation state, which means aluminum must be being reduced. What can you say about the standard reduction potential of aluminum versus magnesium? Hopefully you came up with that the standard reduction potential of aluminum must be larger than that of magnesium. That's why aluminum is being reduced, because its reduction potential is greater. All right, so let's look it up. We're going to look up Al3 plus 3E minus goes to Als. We're going to look up Mg goes to Mg2 plus 2 electrons. You're like, nope, can't do that. I've got to do the reverse. I've got to look up Mg2 plus 2 electrons goes to Mg, because that's just what I got to look up. Okay, here we go. E naught is equal to minus 1.66 volts. That's a very small number, right? It doesn't seem very likely to get reduced. But when you compare it to this guy, minus 2.37 volts, that one's even less likely to get reduced. And so you put the two of them together, and minus 1.66 is larger than minus 2.37. I'd rather owe you $1.60 than $2.17 or $2.37. All right, notice a couple things here. If we were to balance this is not balanced reaction. We don't need to balance it to calculate the cell potential. Oh, wow, that's a wonderful thing, right? We'd end up with 6 electrons, we'd have 2 aluminums, we'd have 3 magnesiums, but it doesn't matter for calculating our cell potential. You don't need a balanced electrochemical cell just to calculate a standard cell potential. Caveat, we're going to calculate non-standard cell potentials later, and there we will need a balanced reaction, but that's only for non-standard conditions. For standard conditions, you don't even need to balance your reaction. It's wonderful. All right, how are we going to calculate our cell potential? Ecell naught is equal to cathode minus anode. What's my cathode? It's where things are getting reduced. Who got reduced? Aluminum got reduced. Minus 1.66 volts minus 2.37 volts. You see how if you're not paying careful attention to these signs, you could really mess up. Okay? Totally easy to mess up. You do that and you get a positive 0.71 volts. that would be literally the voltage that you'd measure if you put it across a voltmeter making this cell. Notice something about both of these numbers. They were both positive. Both of our cell potentials were positive. And in fact, we find that is always true. E cell is greater than 0 for a galvanic cell. Right? Your cell potential is always going to be greater than 0 for a spontaneous cell. It's a great check on your work. Okay? If you did some stuff and you ended up with a negative E cell, you should be looking to check again whether you missed some things up. Okay? Great check for your work. I want to mention one more thing. Okay? Way back up here, we had this one where we took Fe3 plus goes to Fe2 plus. Well, it turns out you can actually go and look in the tables, and there's also one for Fe2 plus goes to Fe solid. And it has a different cell potential than that 0.77 volts. I don't know what it is off the top of my head. So how do we know which one to use? Well, very similar to when we were doing our equilibrium expressions, and we're like, oh, how do we know which conjugate acid conjugate base pair to use when we had Ka1, Ka2, Ka3, is you literally have to look at both things that you have and make sure both of those things are in the reduction potential you looked up. So I know I've got Fe3 plus and Fe2 plus. So I've got to make sure that whatever standard reduction potential I look up has Fe3 plus and Fe2 plus, not just one of them. Okay, very important, because if I look up the one that has Fe2 plus and Fe solid, that's an entirely different reaction, entirely different potential, and might actually go the opposite direction. Who knows? So you've got to make sure you're looking at, okay, I've got Fe3 plus and I've got Fe2 plus. Great, I need to look up that one. Or I've got Fe2 plus and I've got Fe solid. I need to look up that one. Right? Fe, I always say Fe. I don't know why. It's not like iron is harder to say or anything like that, but I always say Fe. So iron 3 plus, iron 2 plus, or iron 2 plus and iron solid. Make sure you've got both of the things that are in yours, not just one of them. All right, that is how we calculate our cell potentials. Our cell potentials will always be positive for spontaneous cells. So unless somewhere I'm telling you we have what's called an electrolytic cell, which we'll talk about later on, you always know that if I calculate a cell potential, it should be positive. So like I said, people make tables of these things. You should be familiarize yourself with the table that you're going to be using on tests and things like that. The table always starts with fluorine. Why fluorine? Well, if you remember, fluorine is the most electronegative element on the periodic table. It loves to be F minus. It loves to be reduced. And so it has the largest standard reduction potential of any element on the periodic table of 2.87. Okay? But then you go all the way down to the bottom of your table, and you've got lithium with a minus 3.04. And so what is lithium? Lithium is very electropositive. It's the most electropositive thing on the periodic table. It loves to lose electrons. So you look, right? 2.87 is close to 3. Cathode minus anode. Fluorine gets reduced. Lithium gets oxidized. 3 minus a minus 3. The best battery you can possibly make in the world is a 6-volt battery. And yet you can buy a 9-volt battery, and yet you can buy a 12-volt battery, and you can buy other voltage batteries. So what are they doing in there? It's like magic? Well, it turns out no. What you can do is you can actually stack batteries on top of each other. So the terminal end of one battery is the start of another battery, and then the voltages add up. You put them in what's called series. And so the voltages add up. And so if you want a 12-volt battery, you put in a bunch of 1.5-volt batteries until you get to 12 volts. And that's how it's done. All right, so we can look at these tables and we can calculate the cell potential for any combination. We can say, oh, I'm gonna make a battery out of iodine and lead 2 plus there, and you say, okay, I'm gonna calculate that cell potential. It's gonna be 0.54 minus minus 0.13. Well, it helps if I make my dots and my lines there different. There we go, 0.67 volts is gonna be my standard cell potential for that. Really, really easy to use, and a great way of calculating these cell potentials. All right, so I'm going to give you a chance to do some of these right now. So what's the cell potential for this voltaic cell? We've got silver going to silver solid, lead going to lead solid, and our standard reduction potentials for each one of them. We know that both of them can't be reduced in this cell, but we give standard reduction potentials because that's just what people give. Now, you have to look down at your cell and see what's actually going on in order to calculate the cell potential for this voltaic cell, right? Voltaic, galvanic, spontaneous, synonyms, right? Go for it. Okay. what'd you come up with? Well, hopefully you said, let me look and see what chemistry is going on. I know, just that phrase just totally went through your brain. Let me look and see what chemistry is going on in my cell. I've got my electrons going this way, so this side must be my anode. It must be being oxidized. So I've got lead going to lead 2 plus 2 electrons. And on here, that must be my cathode. I've got Ag plus going to Ag solid. You're like, wow, he does that so fast. And 1, I've got notes. 2, I've been doing this longer than many of you have been alive. Okay, so yes, I can do it really fast. It will take you longer to figure those things and think those things through. Don't feel bad. Don't be like, wow, I'm not as fast as the professor. Okay, if you were fast as me, then I'd be out of a job. Okay, be slow. It's okay. So what are we going to do? Right, cathode minus anode. Which one's the cathode? Where is something getting reduced? That's my silver. Okay, so what's my silver? Cathode 0.91 volts minus my anode 0.13 volts. Remember, even though it's my anode, I don't, oops, I should put I did change the sign. I was going to say I don't change the sign when I forgot to actually put the sign there. So I put a negative 0.13 volts. I don't change the sign. Why? Because that negative sign, the cathode minus anode, it changes the sign for us. So I always just use standard reduction potentials when I'm using cathode minus anode. So 0.91 minus 0.13 gives me a 1.04 volts. And even when I balance that, silver's supposed to get a 2 on it because they're going to have twice as many silvers. I don't take that into account at all when I'm doing it. I just get a positive 1.04 volts. Remember, you should always get a positive number for your standard cell potential for any cell that happens spontaneously. Whew, that was a long one. Lots of stuff in there, lots of things to think about. But essentially, it comes down to one calculation. Cathode minus anode. Just look it up. Awesome. Thanks so much for listening, and have a wonderful and beautiful day.